Today we are going to continue our discussion about the color blindness. So I already introduced you the principle how the image was formed in your eyeball in the previous lectures. So what happens is that the light will enter into your eye through the function called the cornea. And this function, this part, will behave like a lens, so the light will be refracted and converged at the region called the retinal cones. So the image will be formed here and be transmitted, converted to the signal inside the nerve. And the nerve will pass the message or the information to your brain, and now the image was formed. But however, if the process doesn't run smoothly for some kind of color, then which means your eye is color blind to that particular frequency of the light. So now we can combine all the things we have learned so far. We know that this one shows you that depending on what kind of color of light is provided, then when you combine the red, for example, the red and blue, you will form a magenta, the color. Or if you combine red and green and blue, you will form the white light. So if your eye is red deficient, so-called the protons, you can see that if you compare with a normal one, the red light is the signal cannot be transmitted smoothly in your eyes. So they will look more like the green or dark green. So if you look at this strawberry, if you have a good color vision, this is what we are going to see. They are very dark red. But for the people who are red deficient, you see, this is the color of the strawberry they are going to see. So let's use the flag of the United States as a second examples. So you can see that the central one is for the normal persons, so which means they can transmit the color of the red, blue, and green successfully in your eyes. But if you are red blinded person, then you are going to see the flag on the right hand side here. You can see that the regions with the red strips, now you will look green to them. However, if you are the green blind persons, the left flag is the one you're going to see. And you can even tell that the strip is even redder than the real one. Then the central one is you are blind for all the color, then ideally you're going to see only black and white. But what I'm going to point out is, what is the true color? It depends on the persons, and no one can really tell you what is the true color of their items. It depends on what kind of light and message was passed to inside your eyeballs. So you probably already noticed that I keep mentioning about the illusions. So when we're talking about when you're standing on the wave scale, the value there is also illusions. And the color you see is also illusions. So what is more important in our life is that our personal identity. We should try to understand what kind of person we are. All this kind of the message are all from other people's point of view. They might consistent with your ideas, they may not. But the most important thing is what kind of person you are. You have to truly understand yourself. So now let's go to study the second topic, the rainbow. But in order to study the rainbow, I have to define a quantity so-called the dispersions for you. The dispersions. What is the dispersions? We know that the white light is composed of different kind of frequency of the light, from the red, yellow, green, blue, violet. So they all have different kind of frequency. People find out that the index of refractions for different kind of frequency is different when they enter into a prism. So the principle is that the higher the frequency, the higher the index of refractions. So you can see that when the white light enters into the prisms, the frequency which is bended strongly is the violet one. The frequency which is bent less is the red one. But after the refractions, which is also the dispersions, you can see that the light, the white light, is spread out as a spectrums. And this spectrum is actually consistent with the rainbow. And this is the concept of the dispersions. So now let's try to study about the rainbows. So rainbow is formed also through the principle of the dispersions. So what happens is that, so light will comes out from the sun, and they will interact with the water molecules in the air. So if you focus on one of the water molecules in the air, you can see that follow the rate of the sunlight, they will enter to the drop near its top surface first. And you will find out here there's a first refractions happens. Then now some of the light will be reflected, but it is not shown in the figure here. Then at the first refractions, the light is dispersed into the spectrum color. So you will see that after the first dispersions, they already spread outward. So the red one is being deviated the less, and the violet is deviated the most. Yeah. But this is only for the first one. And when the light reaches the opposite side of the drop, each color is partially reflected out into the air and partially reflected back into the water. So this reflection back is partially, then now after that, arriving the lower surface of the drop, each color is again partially reflected and partially refracted back into the air. So this is the second refraction that happens, and once again the light will be spread out the second times. And therefore you can see that apparently the red light is reflected less and the violet one will be reflected most. So you will see that there are spectrum coming from this water droplet, but only the one of them, which is the red one, will enter into your eyes. But how do we see the rainbow? So the principle is that the same fact will happen for other water molecules, other water drop in the air. So in order to see the red light, you need to have this kind of reflections from a water droplet at higher latitude in the space, in the air. And the violet one will be the refractions from the water droplet in the lower latitude. So what this means is that in order to see the red light, one must look to a drop higher in the sky. So therefore, the color red is seen where the angle between a beam of the sunlight and the dispersed light at 42 degrees here for the red light. And for the violet to be seen, the angle is about 40 degrees. So now, in order to see the rainbow, this is the range of the angle your eyes should point it to, from 40 to 42 degrees. Then you can see the spectrum of the rainbow. And in these spectrums, the red color will be on the top and the violet will be on the bottom. So what you are going to see is this. You're going to see a rainbow. You see, the first one is the so-called the primary rainbow, and on the top it is the red one, and at bottom is the violet. So when the water droplet falls, all the colors of the rainbow can arrive at eyes. So you can see down probably from these pictures that when the water droplet is falling downward, then they can show you that different color of the rainbows. But people may notice that there's a second layer of the rainbow here, and they are wondering what it is. So this is the so-called the secondary rainbow. So the secondary rainbow is just 1/10 of the intensity of the primary one. But let me explain to you what is the secondary rainbows. So the same principle. So some light will enter into the water drop. So they will first be refracted. But now you will see that they have two reflections happens inside the water drop. So that's the reason the secondary rainbow is weaker, much weaker, because they have two reflections, so they will lose the energy, and also two refractions. And now, because of the two reflections, you can see now the water droplet at a higher altitude, they will give you the violet, and the water droplet at the low air, they will give you the red color of the light. So the spectrum you are going to see for the secondary one will be in the opposite order. So this is the primary rainbows. So it is red on the top and violet at the bottom. But for the second rainbow, it is much fainter, yeah? But you can see the order of the color is totally opposite. It is the red at bottom and violet on the top. So this is better using the same fact principle we studied before, reflections and refractions. And depending on how many times of the reflection happens, it determines the intensity of the rainbow and also the relative altitude of the rainbow. So now let's have our first conceptual quiz today. So which of these will not exist if light does not show in the transparent materials? So the transparent material, remember, it means that the light can passing through. So the answer is O will not be. So rainbow, as we see, it is water drop place the transparent materials. And mirage, it is also the same. And the magnifying glasses, which is the lens, place the transparent materials. Now let's try to study the last topic for the chapter 11. So it is about the polarizations. What is the polarizations? So let me use the electromagnetic wave as an example. We know that when the electric field oscillates, or you can understand in terms of electric charge oscillates, it will produce an EM wave. So the polarization is the directions of the fluctuation of the electric field. So for example, if the electric field oscillates up and down, then you will find out, or you can define, this is the polarizations of the electromagnetic wave. And you will ask that, how about for the longitudinal one? So the answer is, there is no polarization for the longitudinal wave. It only happens for the transverse wave. So the second one is for the wave propagate along the string. Yeah? So apparently, you can vibrate up the string up and down or left and right. But the wave is propagate all to the same directions. But now the polarization is different. This one is up and down and this one is left to right. So it is polarized in a different way. So to conclude, it is that wave in the same plane as the plane of the vibrations. So this is how you determine the polarizations of a wave. Now let's try to study a bit more. This is unpolarized light. What is unpolarized light? So which means that the vibration produced light are in the random directions. So sometimes they are up and down, sometimes left and right, or in arbitrary directions. So we can use the figure B to represent that. So there's no unique direction of vibration or electric field. We say this is the unpolarized light. But for the polarized light means that they have a unique direction of the polarizations. So how did you connect the unpolarized to the polarized light? So we are going to study this one in our next video lectures in the part 2.